The precise definition of a limit, Part 1. Before we get into the exact definition, let's take a look at some absolute value inequalities. These are some useful properties of absolute value inequalities. If you're not familiar with them, you might want to pause the video and take a screenshot real quick. Make sure that you understand where these are coming from. Understanding the precise definition of a limit requires also understanding how we represent distance and error using absolute value inequalities. So let's take a look at this one. We have the absolute value of x is less than 2. We want to go from this absolute value inequality to a compound inequality. So we will have negative 2 is less than x is less than positive 2, which we can then graph. So we have an open circle at negative 2, an open circle at positive 2, and then we need to shade in between because x is between negative 2 and 2. What you might notice is that the center of this graph is at 0, and then the distance between 0 and the boundary, so between the center and the boundary, is 2 on either side. Now let's take a look at what happens when we add or subtract a number on the inside of the absolute value. So we'll still want to convert this absolute value inequality into a compound inequality. So we have negative 1 is less than x minus 2 is less than positive 1. And we're still not quite sure how to graph this. We want to make sure there's just an x in that center bit of this compound inequality, so we'll add 2 to each piece in order to isolate that x. So now we have 1 is less than x is less than 3. So we have an open circle at 1, an open circle at 3. And then we shade in between because x is between 1 and 3. Now, the center of this is at 2, which was that number that we subtracted from x. And the distance between this center and each of our boundaries, I just saw 3, so I wrote 3, is 1, which was that number that was on the outside here. And that's important to notice that the center is what we're subtracting from x, and that the distance is what we are less than. This inequality is slightly different because rather than just having an x, we have this 5x. Luckily, 5 is a common factor between 5x and 10, so we can factor that out. You just want to be careful because this is the absolute value of 5x plus 10, so when we factor that 5 out, we also want to put it inside absolute value bars. So we have the absolute value of 5 times the absolute value of the quantity x plus 2 is less than 15. The absolute value of 5 is 5, so we have 5 times the absolute value of x plus 2 is less than 15, and then we can divide both sides by 5. So we have the absolute value of x plus 2 is less than 3. Now we can convert this to a compound inequality. So we have negative 3 is less than x plus 2 is less than positive 3. And we can subtract 2 from each piece. So we have negative 5 is less than x is less than 1. So we have an open circle at negative 5, an open circle at 1, and we shade in between. The center of this is at negative 2. And then the distance between the center and each of our boundaries is 3. If we look over here at this part of our absolute value inequality, we can see that this would be equal to the absolute value of x minus -2 is less than 3. So we can see that the center is definitely whatever number is being subtracted, and that the distance between the center and the boundary lines, or boundary points, is whatever is on the outside. So whatever we're less than. We can use these patterns to quickly write the absolute value inequality that can represent the graph. So if we take a look at this, halfway between -5 and +3 is -1. And the distance on either side of -1 to the boundaries is 4. So this will be the absolute value of x minus -1 is less than 4. Now we can use those properties again. So this first open circle is at -1 and 5/10. The second open circle is at 2 and 5/10. And halfway between would be at just 5/10. And then we can find the distance between the center and the boundaries. So the distance between 0.5 and 2.5 is 2. And the distance between -1.5 and 0.5 is also 2. So we have the absolute value of x minus 0.5 is less than 2. And this is how we use absolute value inequalities to describe distance. So you're going to see this little piece of symbols here a lot in the precise definition of a limit. And what this basically means is when you have the absolute value of x minus a, that means the distance between x and a is less than whatever this guy is. This is a delta, the Greek letter delta, and we're using that to represent the greatest distance. So we want the distance to be between x and a to be less than delta. So that means that we're going to be centered at a, and then we have an a plus delta, because that's the furthest away from a we can go on that side, because we can only be delta away, and then we have an a minus delta, because we can only be delta away from a. And the distance between a and each of these boundaries is that delta. So it's just a way of having a center and describing how far away from it we can be. We can also use absolute value inequalities to look at vertical distance. So here we have our 1 as our distance, or in this case we'll call it error when we're talking about vertical distance. And then we have f of x minus 2. So that means we're centered at 2. So we're centered at 2, and we're 1 away from 2 on either side. So we have an open circle at 1, an open circle at 3, and we can be anywhere between those. And if you wanted, you could show this by converting this to a compound inequality. So we have -1 is less than f of x minus 2 is less than 1. Then we can add 2 to each piece to isolate our f of x. So we have 1 is less than f of x is less than 3, which is exactly what we graphed. And then we can use those properties again. So let's rewrite this so that we have subtraction on the inside. So that would be f of x minus negative 3 is less than 2. So that means that we are centered at negative 3. And the furthest away from negative 3 that we can go is 2. So that would be negative 1 and negative 5. So we have an open circle at negative 5, an open circle at negative 1, and we can shade in between. And we could also show this by solving. So we can open this to a compound inequality. So we have negative 2 is less than f of x minus negative 3, which is just plus 3. That's a little easier for our solving. Is less than 2. Then we can subtract 3 from each piece. So we have negative 5 is less than f of x is less than negative 1, which is what we found and graphed. So we can also use absolute value inequalities to describe error, which is just the same as distance, but we're talking about f of x. So if we have the absolute value of f of x minus L, that means we're looking at the distance between f of x and L. So L is where we're centered, and we want that to be less than, and this symbol here is the Greek letter epsilon, and that will be that maximum distance between f of x and L. So we're centered at L, and the furthest away from L that we can be is epsilon. I don't quite like where that went. There we go. So that means that the furthest up we can go is L plus epsilon. The furthest down we can go is L minus epsilon. So we can be anywhere in between L minus epsilon and L plus epsilon. And that is how we can use absolute value inequalities to describe error. And you want to feel comfortable going back and forth between the absolute value inequality and the graph, both for f of x and for just x.